world of networking. So you're assuming that people who are talking, if they want to make rules and say, now it's your turn to talk, they're using the same medium, which means that if two people at the same time says, now it's your turn to talk, nobody will hear anything, right? So there's a single shared medium for sending data. As for any protocol traffic, you need to have to control who sends data and when, okay? Any questions about the problem? The basic problem is clear? So what is ideal MAC protocol? Let's say you have a channel, a shared channel that can carry 100 megabits per second, and you have 4 people sharing it. Number 1, let's say A, B, C, D. So the 2 properties we look for, the first 2 are this. If there is nobody else transmitting, for example, if these guys are asleep and only A and C want to talk, there's 100 megabits in the space. So A and C should be able to talk at the full bandwidth at 100 Mbps, right? It'll be nice that we don't have to worry about sleeping people. So that's the first thing. Second, more important, what if everybody wants to send? What if all A, B, and C, everybody has lots and lots of stuff to send. They have long queues of data they want to send. Now you want to share it such that everybody gets a fair share and no bandwidth is wasted. So you'd like everybody, A, B, C, and D, to be able to send, in this case, at 25 megabits per second. That's the best you can expect if everybody has to get something. So you'd like basically fair sharing and no wastage. Okay. So that's idealistic, but you can shoot for that. The other thing you want is you want things to be fully decentralized. You shouldn't have to send any special communication or count on special clocks and things like that, that everybody, you can't say A sends between 2 o'clock and 2:01, B sends at 2:01 to 2:02, because that assumes that everybody has a synchronized clock. It's exactly the same, and that's actually a non-trivial problem at microseconds at really fine granularity. So yes, you could build a synchronized clock that everybody has, but you'd like that not to be the case. You'd like that you don't have to synchronize. You can somehow send when you can send, and everything will work. Okay. And of course, it's always nice to have simpler protocols. Any questions on our ideal goal? So this is a reference. As we go along various protocols, we will try to measure them up against this ideal protocol and see where they stand. Okay. So there's 3 classes. You partition the channel into equal parts. That's one protocol. Random access, where everybody tries to send simultaneously, and if there's a problem, when problem means there's a collision, when 2 people send at the same time, you try to recover from it. And the third one is that you have some protocol where you somehow can say, now it's A's turn, now it's B's turn, now it's C's turn, and so on. Okay. So I'm sorry? Some of them are same as time slots. So we're going to discuss each of these in a little bit more detail. So not all of them follow the goals of the ideal protocol. Okay. So the channel partitioning is actually the same as what we saw in the first chapter of time slots. So we have seen this already in the first chapter. Channel partitioning is what we call TDMA, or one of the ways of channel partitioning is TDMA, or time division multiple access. So what you do is that you have a block of time called the frame. It's kind of using the term frame again in a slightly different context. So you have 6 people who want to send data. So you divide the frame into 6 parts. Frame is a unit of time. So if the frame was 6 milliseconds, then you say the first millisecond is to 1, second millisecond is for 2, third is for 3, and so on. So each station gets a fixed length slot. Okay? And you repeat every 6 milliseconds. So basically, the first one sends, let's say, millisecond 1, then 7, 7 plus 6, 13, 13 plus 6, 19, and so on. Second sends at 2, 8, 14, 20, and so on. So the good news is once you have these rules, it's very simple. Everybody has their schedule, and they can send. The bad news is first you need synchronization, which we do not like. Everybody has to agree when slot 1 starts, when slot 2 starts. And so that's not desirable, but it's part of this protocol. And the second thing is unused slots go idle. This is a hard division. Here you see that 2, 5, 6 have nothing to send. Okay? So those slots are wasted. So each of these stations gets 1/6 of the bandwidth. Even if nobody else is sending anything, you still get only your share because you made a hard division. Okay? So that's one protocol. Obviously not the best. Okay? Any questions? This is actually something we saw before. And instead of time division, you can achieve exactly the same thing with frequency division, multiple access. So here what you do is you divide your frequencies into bands 1, 2, 3, 4, 5, 6. And here you see that the frequency band 1 is busy, frequency band 3 is busy, 4 is busy, and these are empty. And again, if that was the scenario, half the bandwidth is getting wasted because only 1, 3, 4 are sending, but there's a fixed assignment of frequencies which includes 2, 5, and 6. And the properties of this from our perspective are exactly the same as time division, multiple access, really a difference in technologies that are used. Okay. Any questions on TDMA, FDMA? Okay, those are pretty straightforward. The more fun protocols are the random access protocols. And the key is when you're doing random access, collisions will happen. How are you going to find out if data has collided? And what are you going to do about it? That's the key. If collisions never happen, you send data randomly, everything got there, there's no problem. When collision happens, you need to know it happened, you need to send the data again. So that's the basic idea. And we are going to look at a couple of these MAC protocols. The first one is something called Aloha, and it has 2 versions. There is slotted Aloha and unslotted Aloha. Okay. So, well, the first question is, where did this protocol come from? Anybody wants to guess? Hawaii? What made you think that? What's that? Okay. What is besides that the word aloha is from Hawaii, what is unique about Hawaii that might be relevant for communication? It's an island? Yeah, so it's a whole bunch of islands, right? And suppose you wanted to build a communication system between those islands, and you can't run telephone wires under the sea and so on. So it's very attractive to have some kind of a radio-based communication between the islands. So that this is really a wireless, wide area wireless protocol which they developed, I think, at University of Hawaii for communication between the islands. Okay. So again, Aloha does not follow many of the desirable properties that we talked about, but this is what it does. The whole bandwidth is divided into slots. For slot